Welcome back to the final of our section from Chapter 1 on vectors. Vectors, we've been stating all along, are speed, but with a direction attached to it. So let's distinguish between the term scalar quantity, as in our first bullet, versus a vector quantity. It's telling us that a scalar quantity is when a quantity is reported with a single number and a unit. It clearly tells us that we can have positive, negative, or even a zero value. I could be traveling 50 miles per hour. I could be traveling at 0 miles per hour. So I'm looking at a number with a unit. If I want to turn that speed into a vector quantity known as velocity, I have to indicate direction. The size of the vector is called its magnitude. If I'm traveling 50 miles per hour west, I've now turned my speed into velocity, which is a vector. And vectors can be graphed. Vectors are represented by an arrow where the length of the arrow represents its magnitude. And let's take a peek at that a little closer. If you have your book open like I do, I'm looking at vectors beginning on the bottom of page 17, but quickly turns over to page 18. So looking at vectors representing a vector quantity with a symbol by using an arrow over the top of it. For instance, if I have a symbol R representing the radius or whatever I might be looking at. I have a delay in the screen. I'm just kind of waiting for that to catch up as I'm writing. Oh, I sure appreciate your patience in this video. My screen is not advancing. Stay with me, please. It's just going to take a quick minute for the program to catch up. There it is. Thank you. Vectors represent a quantity that are represented with a symbol. In any symbol, I'll just use a symbol R. You will see that a vector is placed over the symbol, always pointing toward the right. I could have a vector as a capital A. The vector over the symbol shows the magnitude of this particular measurement, representing a vector quantity. Handwritten work must have drawn arrows over all symbols that represent vectors. The text reassures us that that gets tedious, but pretty soon it becomes second nature. There's a big difference between R, a scalar quantity, and R, a vector quantity, and we must let the reader know which one is which. A vector quantity has both size and direction. How far, how fast, and in which way. The vector quantity includes all three pieces of information. The size or the length of the vector we know is called its magnitude, and we graphically represent a vector as an arrow, as illustrated in many of the following examples. Let's begin taking a look at those examples. Here we have a car being represented by an arrow. Since it is a vector, the quantity requires both magnitude and a direction, being represented with an arrow. Graphically, the speed of our race car turns into a vector quantity known as velocity as soon as we include the direction and the magnitude of that particular value. We could call it 100 meters per second. That's its magnitude. To the left, heading away from the origin in the west direction. The boy pushing his friend with a force of 25 newtons to the right. The term newton is a metric unit for the measurement of force. Little boy is pushing another kid on a swing with a certain amount of force. The force is measured in a newton. Since it is moving in the east direction, the positive direction, we've turned the force into a magnitude or a vector indicating the direction is right. Displacement vectors. Very critical here. Again, this is talked about middle of page 18. Displacement vectors, they start at an object's initial position and end at an object's final position, regardless of the path that the object took to reach the final destination. The shortest distance between 2 points is a straight line. That straight line represents a displacement vector. Vectors are given arrowheads to show the direction in which the object moved. It doesn't matter what the object did in between these 2 points. The displacement vector is simply showing the shortest distance between the initial point and the final point, the destination when the object arrived. The displacement vector spans successive particle positions. So an object's displacement vector is drawn from the object's initial position to its final position, regardless of the path it followed. Draw the straight line between the 2 points, and you've shown a displacement vector. Let's read a little bit about Alice and see what it asks us to do. Alice is sliding along a smooth, icy road on her sled when she suddenly runs headfirst into a large, very soft snowbank that gradually brings her to a halt. Draw the motion diagram for Alice, showing and labeling all displacement vectors. Now, a couple of very strong words here, letting us know what the diagram will end up looking like. Very soft snowbank. In other words, poor Alice, if she had been traveling down a hill or along a smooth road and came upon an object that dead stopped her in her tracks, we would see constant velocity and then ultimately it would stop. She wouldn't be able to move forward if she crashed into something that prevented her from just gradually slowing. So that's allowing us to predict she had a constant velocity. The motion here is at constant speed because I can see very much the same length. Then she hits the snowbank. When she hits the snowbank, you see a deceleration. Notice the magnitude of our displacement arrow is getting shorter and shorter and shorter as she gradually came to a halt. Notice the displacement vectors are getting shorter and shorter, so this is showing how she is slowing down. Same magnitude represents constant velocity. A shortening of the arrows shows a slowing down of her velocity. When we're adding displacement vectors, as if any vectors, they are very different than adding scalar quantities. In other words, if I had 2 numbers with like units and they are scalar quantities, meaning no direction given, I simply add them together. 12 feet plus 6 feet is 18 feet long. This is just representing adding some lengths. 12 feet is a scalar quantity, does not give direction. 6 feet is a scalar quantity, there's no direction. I can simply add the numbers if they have like units and report out an answer. But displacement vectors, or any vector quantities, because of direction, is a little more involved when we begin adding vectors. Here's an example, and again, if you're looking, this is the top of page 19 talking about Sam. Sam undergoes 2 displacements. If this intersection of a street, 12th Street and Vine Street, for the point of origin, shows Sam's journey beginning along an x-axis coordinate here from the origin, and he heads a certain distance heading east. Notice here, we're now getting familiar with the vector quantity D1 representing distance, but now giving us direction. He is heading east of the point of origin, and I clearly see the little arrow above the symbol representing that it is a vector quantity. He traveled a specific distance called D1. He stopped. From there, this point of origin begins the second leg of his journey. He started heading in this direction to a final destination. Notice D2 is a vector quantity. Not only does it indicate a distance he traveled, it is also pointing in the direction. He is heading northeast of the point of origin. Northeast of the point of origin turns it into a vector quantity. How far did Sam travel in terms of his displacement vector? When we write out the two legs of his journey, there's a very specific step-by-step way to show where he landed. The vector quantity known as D1 along the x-axis, heading due east means straight along the axis, and we reached a point. The origin of one vector is placed at the end of the head of the arrow for the last vector, tail to end, tail to end. So we're looking at placing the tail of B, or the tail of our second journey, at the tip of our first vector quantity. The tip of the arrow, the tail of the arrow. He headed northeast for a vector quantity known as D2. We're being asked to solve for the net displacement. The net displacement says it doesn't matter the journey he took. I want to know from the point of origin to the straight line ending point, regardless of the path he took. We call that the displacement vector. When we find the displacement vector, we've created a triangle, and we can kind of foreshadow a little trigonometry involved to find the direction he ended up. So since he consisted of two legs represented by vector quantities D1 and vector quantity D2, his trip as a whole is represented by D net. The net of his displacement is the sum of the two individual vectors D1 and D2. Let's break that down and talk about the figure on page 19 that matches this particular slide. Vector addition obeys different rules from the addition of two scalar quantities. The directions of the two vectors, as well as their magnitudes, must be taken into account. We do that by putting the tail of one vector at the tip of the other vector. That's how we add the vectors. If we have to add vector A and vector B together, vector A and vector B added together, step 1. Draw vector A with the correct magnitude. Step 2. Place the tail of vector B at the tip of vector A and draw its correct magnitude. To find the displacement arrow, the displacement vector, start at the origin of A and bring yourself to the tip of vector B. A plus B shows regardless of path. We wanted to know origin of the first leg of the journey and the final destination from the second leg of the journey. Journey 1 would be vector A, journey 2 would be vector B. The displacement vector, the sum of A plus B when I join the vectors tip to tail. Oh, I missed a page. Let's focus here then on the trigonometry, and it may be review for most of us, but it's worth taking a quick peek at some of our formulas just to refresh our memory. The formulas are provided for us on the bottom of 19, that primary tool to help us predict vector addition and resulting angle and so forth. So I'm just going to place my book here and ask you to kind of peek with me at these equations. In a triangle, figure 1.23 is showing a right triangle. The longest side opposite the right angle is called the hypotenuse, abbreviated H. The side opposite the angle, theta being the angle, is known as side O for opposite. The side adjacent to the angle is known as side A. Hypotenuse, opposite, adjacent. With the right angle, triangle. If you know the angle, called theta, and the length of one side, we use trigonometry, sine, cosine, or tangent to find the lengths of the other side. So the little simple trig allows us to solve many problems in physics with displacement vectors. Hopefully, we've had some experience in the background of vector quantities in trigonometry. If we rearrange those same equations, we find this on the top of page 20. Theta is the inverse sine of opposite over hypotenuse. Theta can also be found as taking the opposite of cosine, inverse of cosine, a over h, adjacent over hypotenuse. And theta can be found by taking the inverse of the tangent of opposite over adjacent. Another way of rearranging, just hitting the inverse on your calculator, usually it's second function, the opposite of. So if I see on my calculator sine, cosine, and tangent, put that up a little bit, sine, cosine, and tangent, notice here on the top of it, I see the inverse. Second function sine raises it to the inverse. Second function cosine raises it to the inverse. Second function tangent brings me to the inverse. So that's literally what this key on the calculator would be looking like. Second function sine, second function cosine, second function tangent solves for that particular area. Alrighty, so just a little trig review there. They're probably handy just to have in your notes so you can find them easily. Let's add a displacement vector. Suppose Alex is navigating using a compass. He starts walking at an angle of 60 degrees north of east and walks a total of 100 meters. How far north is she, Alex is a she, from her starting point? How far east? Let's get familiar with just beginning with a model first. Model first, math second. Heading due north is straight up, our xy axes. Heading due east is heading straight to the right direction on our x-axis. We'll call the point of origin the 0, 0 mark. Walking at an angle north of east of 60 degrees is represented by saying if this is east, he's walking 60 degrees north of east. I'll represent that in the center here. It's probably not exactly on, but we get the idea. And walks a total of 100 meters. So from the origin to the end point, we now know that that's 100 meters. So thinking about this point in terms of a vector quantity, notice how I'm putting there, I'll put D1 for the first distance, or just thinking about that vector quantity, we know that it's 100 meters, that's a number, a unit, and a label for direction, 60 degrees north of east. How far north from her point, from her starting point, how far east, how far north, how far east. I'm going to draw in this side of our triangle. This side that I've just drawn in represents, this value here is the distance north. From the x-axis being due east to the ending point of our journey, we're heading straight up in a straight fashion here, that's directly north. The line segment that I'm drawing here represents the distance north. The line segment from the origin to the point we just finished represents the distance east. We'd like to know both sides. So the displacement represented, kind of being shown here, this displacement really is giving us what we called side H, the hypotenuse. The opposite side of our triangle, side O, and the adjacent side of our triangle, side A. We know we know the angle called theta is 60 degrees, and we know the hypotenuse is 100 meters. Let's start then by finding the distance north of start. Let's find side O. I'm just reminding us where we're putting this. If I know the hypotenuse, I know the angle, and I'd like to know side O, I gave it away. We use this formula, sine theta equal opposite over hypotenuse. Sine theta equal opposite over hypotenuse. The sine of 60 degrees is equal to our target opposite over hypotenuse. Rearranging, sine theta times hypotenuse gives us our opposite side. And let's hit together, grab your calculator, and see if we get a common answer. Putting my calculator on, sine 60 degrees times, which we don't have to hit, but we will, times 100 meters equals. And we get a value, and I'll write it down on my calculator just so we can see, 86.6025 and so forth. How many significant digits will we include? 100 meters has 1 sig fig. These bottom zeros here are a magnitude. Sine 60 degrees, 60. This is also a placeholder. But being that we have to give the same number of sig figs as we're multiplying through with holding the place properly, we need to report with 2 sig figs. Looking at this value, we'd round up 87 meters, the distance to the north, opposite side. Let's solve for the distance east, side A. What equation would we want to use to pull out side A? Well, we have, trying to get it on the screen, we know the hypotenuse. We know the theta is 60 degrees. Let's use the cosine and pull out the adjacent side. Cosine 60 is equal to adjacent over hypotenuse. Cosine 60 times 100 meters gives us our adjacent side. Let's hit together. Cosine 60 times 100 meters gives us a value of 50. 50 meters is the correct number of significant digits, and there's our answer. We use trigonometry to find opposite and adjacent sides, knowing hypotenuse and knowing the angle called theta, 60 degrees. Easy enough, my friends. If Anna walks 90 meters due east and then 50 meters due north, what is her displacement from the starting point? Model first, math second. Anna walked 90 meters due east. Let's make this the point of origin, and we'll just say this dot represents 90 meters. So this side represents a value of 90 meters, due east. She then goes 50 meters due north. That means straight up 50 meters. What is her displacement from her starting point? We're adding vectors. Displacement vectors mean I'm going to draw the tail to the tip here. There's vector 1. I'll call it distance 1 is a vector quantity. She then heads due north. Notice here from tip, and I make the tip here from tail to tip. There's vector quantity 2. The displacement says, I don't care the path that you took, from the origin to the final destination, what's the straight line? Adding the vector quantity to find the net displacement, I take vector quantity 1 and add it to vector quantity 2. We're being asked what is her displacement from the starting point. We add the two vectors. So analyzing Anna's motion, we drew the two vector displacements with the tail of one vector starting at the head of the previous one. We have a nice visual representation that we're looking here. What we don't know is the actual value of theta. So we can just place that in as some angle yet to be determined. When we drew the vectors, we're looking at what the triangle is showing us. Anna's distance from the origin is the length of this vector. But again, to have it a vector quantity, we have to indicate the direction. That's where the theta part comes in. That's when we need to know the value. What we're looking at here is something known as the Pythagorean theorem. The square of the length of the hypotenuse of a triangle equals the sum of the squares of the lengths of the sides. I think there's a song in that, isn't there? The Pythagorean theorem, d net, now that's a vector, squared is equal to the sum of the squares of both sides. d1 squared plus d2 squared. There, I got it all written down. Pythagorean theorem. The square of the length of the hypotenuse of a triangle, this is not a right triangle, we don't know that value yet, is equal to the sum of the squares of the lengths of both sides squared. Let's put that into what we're looking for. d net, vector quantity, squared, is equal to 90 meters, d1, squared, plus vector quantity 2 here is 50 meters squared. Pythagorean theorem. The length of the hypotenuse of a triangle is equal to the sum of the squares of the lengths of the sides. Let me hit what we have so far. 90 squared plus 50 squared gets me a number. It's actually quite large. 10,600. Now remember, that's our vector quantity, yet still squared. To get rid of a square, we need to take the opposite. It's called a square root. This vector quantity is the square root of 10,600. So with my answer, I just take the square root. Notice what I did, second function x squared. Put that on the screen better. Second function x squared is where my square root is. Then I use second function answer. Notice that's way at the bottom where your answer key is. Equals. And we get a number. That number on my calculator, 102.9, I'll write it all, 102.956. And that would be a meter. But let's be smarter than that. We've got to consider sig figs. Notice the distance, 50 meters, non-zero digits. 90 meters, non-zero digits. The zeros there are representing the magnitude. To report with the correct number of significant digits, we'll say 100 meters. About 103 meters turns into 100 meters when reported with the correct number of significant digits, giving us 100 meters for the magnitude of the displacement. But we're not done yet because it asks for the vector quantity, and that means we have to report out the direction. But we now know quite a few things. We know the sides. One side is 50 meters, one side is 90 meters, and now we've determined the other to be about 100 meters. I would let this side not determine what I'm going to use because that was an estimation. Let's solve for theta with what we know for sure. Opposite and adjacent are what we know for sure. So I like this formula best. If I'd like to know theta, let's use the tangent. These were the two numbers provided for us in the question, and we wouldn't have to rely on our calculated hypotenuse, which we're estimating. So to find theta, inverse tangent of opposite over adjacent. Theta can be found by taking the opposite of tangent, the inverse of tangent, if you like that better, of opposite, 50 meters, over adjacent, 90 meters. Hit with me to be sure we're comfortable with the key sequence. Here's my calculator just to show the screen. Second function, tangent, pulls up the inverse of tangent. We're taking the inverse tangent of opposite, 50 meters, divided by adjacent, 90 meters, close the parenthesis, equal. And we have an angle that's 29 degrees. Theta is 29 degrees. 29 degrees means what? 29 degrees means that the net displacement is 29 degrees north of east. 29 degrees north of east. So to report out a number, a unit, and a direction for my displacement vector, 100 meters, 60 is the last problem, 29 degrees north of east. We've reported the length of the hypotenuse by using Pythagorean's theorem, and we use the inverse tangent of opposite over adjacent to pull out the degree, the theta, and found it to be 29 degrees north of east. The last thing we'll look at and just kind of comment on are displacement vectors that are lengthening and displacement vectors showing magnitude. The velocity of an object being represented by a velocity vector that points in the direction of the object's motion and whose magnitude is the object speed. So if we're just showing this to remind us that from now on, when we use vector quantities, you'll see the magnitude of that quantity being represented by the length of the arrow. So from now on, you'll see that labeled velocity vectors on motion diagrams rather than displacement vectors. And one of the last things it has us do is to look through an example. Here it represents velocity of vectors thrown at an angle. Jake throws a ball at 60 degrees, measured from the horizontal. The ball is caught by Jim. We're just being asked to draw a motion diagram. What does the velocity look like in a motion diagram? Jake represents a certain velocity, 60 degrees, kind of north of east, if I think of the point of origin, throws the ball, and we begin to see that it slows down till it reaches the peak of the arc. Then it begins to accelerate it as he begins to hit towards the earth. Velocity vectors just showing a motion diagram of a projectile. Tossing a basketball, reaching the peak of the arc, and heading back down. All we're doing is looking at the motion diagram to become familiar with what they're trying to tell us. What information can we glean by looking at the particular drawing? Deceleration reaching the peak, acceleration as it comes down towards the earth, the result of gravity. The last thing we could think about is really just kind of showing the summary. What are some things that we can reflect upon through the journey of Chapter 1? We started talking with the particle model. Particle models represent a moving object, and all of its mass has been concentrated in a single point. The very first leg of our chapter talked about what information we can think pulling out of this particular diagram. We talked about describing motion in terms of the direction. If we have a point of origin, traveling in a positive direction is heading east, traveling in a negative direction is heading west. We found that we could calculate velocity by knowing the change in distance over the change in time. We talked about the difference between a scalar number and a vector quantity. A scalar quantity, a number with a unit, and a vector includes the direction. Vector quantities, those problems are solved with the help of trigonometry. We talked about units and the standard international system of units. I'd highly recommend practicing converting units as you get ready to start the homework. That's one of the skills I know that they had us practice in the homework, is just changing one unit into the form of another. That concludes Chapter 1's lecture. You're ready to finish the assignment in Chapter 1.